Okay, so the last event of today is a discussion on lattice gauge theory, flux tubes, near conformal systems, and more, led by Marina Marinkovic and Anna Hasenfratz. So Marina will start. Thank you.
All right, thanks, Igor. Thanks, everyone, for the invitation to well, maybe spark some of the discussions that we're going to have, although there is a number of also open topics left from this morning. So I expect that we'll have plenty of things to talk about. So, yeah. So, as some of you have heard already, I gave a longer talk on the basics of lattice techniques earlier last week, and I'll highlight here some of the lattice results mentioned there, which we could discuss in the continuation, as well as the talks which we've heard in this conference, which are based on and the lattice gauge theory's approach to discretizing space-time using the four-dimensional Euclidean lattices. So we've heard a talk on Tuesday by Andrea Satinodoro about the flux tube spectrum and in SUN theories. Then we've had a talk by Zoltan Fodor on the mu-G-2 computation, so the computation of the leading hadronic contribution to mu-G-2, and a very interesting talk this morning by Michele Caselle on how flux tubes behave and at finite temperatures. And so the projects I'm currently working on are related to the behavior of flux tubes with the presence of fundamental matter degrees of freedom. So we know that in the large N, so we know that in the pure gauge theory, the QQ bar system would diverge for large, the energy would diverge for large separations, but if we include C quarks in our simulations, then we expect to get string breaking, and this is something that we can compute from the lattice as well. In this case, it's not sufficient to just look at the correlator of the Wilson loop operators, because we have a mixing between the QQ bar state and in the presence of light quarks, also heavy light meson state. So what we need to do is to apply the generalized eigenvalue approach as discussed in the talk by Andreas on Tuesday. And we organize these correlators in a single matrix and then solve the generalized eigenvalue problem, where we need to take into account not only QQ bar and BB bar states, but also the mixing between the two. And the first step in all such analysis is to compute the static potentials. And already there in the lattice, we have a number of technical challenges. Some of them have been addressed with Anna and her collaborators now already 2 decades ago. And they're still in use. So the techniques in order to increase to reduce the noise in the computations of these correlators, which we get in the Monte Carlo simulations. So they go by the name of hip smearing, and this particular way of blocking the neighboring so taking into account not only a particular link which enters the Wilson loop, but blocking it also with the neighboring gauge degrees of freedom in order to get a better signal to noise in the computations of the static potential. And the static potential computed in the Wilson, so computed in the dynamical lattice QCD approach, where where on top of the gauge degrees of freedom, we also use Wilson discretization of the fermion part of the QCD action. Looks something like this. So in the lattices, which we applied so far in our preliminary analysis, the length, the physical length is not sufficient in order to see the flattening of the potential, which Michele nicely showed in his talk earlier today for lower dimensional systems, where one can go to larger length in an easier way. So I've discussed earlier, so I've discussed in a longer talk last week, what is the technical what are the technical difficulties in reaching such large length with high precision in dynamical fermion simulations. It's certainly possible, and it's something we are looking into, but it requires more time than doing it in more computer time, in particular, than doing it in lower dimensional theories. So we work in SU3, but we've seen also earlier this week similar results for SUN theory, so SU4, SU5, done by Andreas and Atenodoro and Mike Tepper, but in this case, with taking into account only gluon degrees of freedom, so without inclusion of the dynamical quarks. So here's just the list of recent work on, and not so recent as well, on string breaking. So this is a topic that has been present for a long time in the Lattice community, first performed in SU2 calculation. Then the Higgs model as well has been studied, so the string tension and the spectrum of the flux tube. And more recently, the 2-flavor and the 3-flavor QCD simulation. When I say for non-lattice experts, when I say 2-flavor simulation, means that we, on top of the gluon dynamics, we take into account the dynamics of up and down quark, and in F equals 3 up, down, and strange quark dynamics are taken into account in the generation of gauge configurations. So not only in the valence, but also in C, we take into account the dynamics of these 3 quarks, and currently ongoing simulations take into account also dynamics of charm quark, but string breaking studies have not been performed in that setup yet. As well as another interesting setup would be the approach where up and down quark dynamics are, so the masses of up and down quarks are not taken to be degenerate. So in the default setting for lattice simulations, up and down quarks are taken to be degenerate. And as we've heard in the talk by Zoltan earlier this week, for precision calculations, such as the hadronic contribution to the mu(T)-2, where we need to know with a sub% precision, one needs to take into account also this effect of isospin breaking, and the fact that both the charges and the masses of up and down quark are not degenerate. So this is something that in this type of studies, where we would be happy to have a result also with the order of 10% or several percent, but not sub% precision, is not yet relevant, but we are looking into including it in our future studies. Then another point I mentioned last week, and I would like to reiterate here, is related to the computation of hybrid static potentials. So instead of simply looking into the correlator of Wilson loops, we may distort the Wilson lines in such a way that we introduce appropriate quantum numbers and get higher excitations of the flux tube. Let me just recall that other than the spin, so we're looking into the parity and charge conjugation quantum number together, and the reflection positivity with respect to the axis which is perpendicular to the one which connects the static quark and antiquark. And this has been done in Lattice as well. So some of my collaborators have been working on this. We've also heard in detail how this computation has been performed by Mike Tepper and Andreas Atinodor over the past decades. So this is an example of the result of such computations, where instead of the correlator of Wilson, of simple Wilson loops, we look into the correlator with of loops with higher, with other quantum numbers introduced in such a way by deforming the Wilson line. And these static potentials can be used also in the direction of the which was of the applications which were discussed this morning by Satoshi Hosaka in the first talk. So we could get results for phenomenological results which can be applied, which can be confronted with the recent LHC predictions by using these hybrid potentials in order to solve Schrödinger equations for the BB bar or CC bar states, relying on the Born-Oppenheimer approximation. And this is something which has been used for a number of years already in perturbative non-relativistic QCD, and only recently became also a topic of lattice computation, since we can compute these hybrid potentials featuring in this Schrödinger equation for the heavy quarks rather precisely on the lattice, as you've seen in this example and also in the examples discussed earlier this week. So we had a very nice discussion of the recent lattice results in the talk earlier this morning by Satoshi Hosaka, and the comparison with the quark model. I'd just like to add some more recent references as well, which study tetraquarks on the lattice, and unfortunately do not yet find any convincing evidence for deeply bound states beyond the states which were confirmed in earlier lattice studies, which contain B bar, and light quarks or light and strange quark. So these tetraquark configurations have been confirmed in lattice studies. I'll stop here. So this is a slide which I promised to some of you when discussing the possibility for you and your students, even though in case you're not doing active research in this field, to perform your own, so to test your own ideas in lattice QCD. So there is a number of publicly available codes which can be downloaded, and it's very simple to start up your simulations and to test your ideas, at least in pure gauge theory. So for including dynamical fermions, as we discussed last week, there is a high computational demand. So they are computational demanding, and one needs a supercomputer in order to invert the Dirac matrix sufficient number of times in order to get independent configurations with the algorithms which are currently available. But if one is interested, let's say, studying SUN or U1 theory, then this is something that can be done on a laptop nowadays or on a desktop. And in particular, with the developments in the graphic cards and so on, one already has a little supercomputer in their own office nowadays, and with proper explanations which are provided in these publicly available codes, one can also test ideas on your own without necessarily waiting to and get on top of the to-do list of one of our lattice colleagues. All right, so I'll stop here. And I'll let it to Anna to discuss. So is she connected?
Yeah, actually don't see.
Okay. All right, so we have spoken a few times during this in preparations for this, and I know that she wanted to discuss her recent work on conformal systems. So Anna and her colleagues have been studying also higher representations and larger number of fermions in the simulations in order to attempt to try to find the conformal behavior and to explore the conformal, near conformal behavior in QCD-like theories. So if you have any, I
guess we just have to proceed with the discussion then. Since she did. Yeah, maybe we should open floor to discussion of. Also, I think it's fair game to ask questions about the earlier talks today that weren't finished. Okay, so I see Marek already.
Marina, hi. This was a very nice review. And one question about application of lattice methods to these BB, U bar, D bar tetraquarks. The Compton wavelength, the mass of a big quark is about 5 GeV. So the Compton wavelength is about 1/25 of a Fermi. What this means is that one cannot directly simulate big quarks in lattice QCD at present, because if you want a box with the size of, say, 2 or 3 Fermi, you need 50 or 75 lattice-sized sites in each direction. So people have invented clever tricks to bypass this limitation. To what extent are we sure that these tricks do not introduce some systematic effect?
So thanks for this question, Marek. So it's true. I mean, so if we would try to simulate the B quark directly in the lattice, the finite volume effects, it wouldn't just fit in the boxes that are currently available. So the finite volume effects would be overwhelming. So what we're doing there is well, effective field theory approach, but lattice effective field theories are constructed for the inclusion of B quark, and similarly as the lattice method itself, it is systematically improvable. So the simplest approximation is the static. So the static approximation, and that one we know that has systematics which cannot be directly controlled, since the big quarks are not infinitely heavy. But then at the next order and the leading order and so on. So basically you can we expand in 1/, mass of the big quark in a specific way such that it's compatible with the lattice approach. So when done correctly, it's systematically improvable as well. It's just technically difficult to include these higher order corrections, and not all lattice approaches practice that.
So can one quantify at the present state of the art of these corrections that have been computed for the effective field theory on the lattice, what are the error bars on the binding energy?
For which system in particular?
For the system of 2 big quarks and 2 light antiquarks.
2 big quarks and 2 light antiquarks. Yes. So I haven't performed this calculation myself, but in the reference which I cite here, these error bars are included. So it's a combined error of continuum extrapolation, all the other details that I've discussed in a longer talk before. So infinite volume extrapolation, continuum extrapolation, and so on. I do not have the number on top of my head, but it's included as the systematic error of the predictions which are given there.
The one specific reason why I ask this question is that there are significant differences between various lattice groups. And so the question is, are they consistent with each other given these error bars?
So within the error bars, they should agree. But I mean, I don't have them on top. Yeah.
If they do agree or not, because it's not clear that there isn't some effect that beyond what they estimate the error bars are. I mean, there is quite a scatter of lattice results for the binding energy, right?
Yeah. Yeah, but again, then the only reason for that can be that, so I wouldn't see anything fundamental behind it, but that the systematic error estimation has not been completed. So many of these results come on a single lattice spacing, which means a single value of the cutoff, and you need to remove the cutoffs to take the continuum limit. And this is technically rather expensive. I think that being motivated with the future experiments that this will be done. But so if one compares the different lattice results and the fixed value of the lattice spacing using the different discretization of the fermion part of the action, also different approach to effective field theory is relying on different discretization of the Dirac operator. It's natural to get the results which are apart from each other. If the error is properly estimated, then they have to be on top of each other.
No, nothing mysterious. I was just asking about the state of the art. Where do we stand? Okay, thank you.
Sounds like more work is needed, right? Okay, maybe we can move on to the next question, Volodya Kozakov.
Hi, Marina. I'm interested, as you know, in large N and 1/n corrections. You mentioned somewhere in your introduction that the simulations have been done for higher N's than 2 or 3, and also with dynamical fermions. Can you compare the results, say, for N equals 2 and 3, and for higher N's to estimate the role and the size of 1/n corrections, and whether, for example, 1/n square correction would be already good in pure gluon dynamics to fit all these results, or you need more, and also the same about dynamical fermions, how important they are.
All right, so let me split into two and already answer the second question. So the one with dynamical fermions, this hasn't been explored in such detail for higher values of N. So precise studies have been done mainly for SU3. So there it would be hard to talk about 1/n corrections. Now, N square even. Now for the pure gluon dynamics, yeah, so we've heard in the talk of Andreas on Tuesday that computations of flux tube spectrum have been done, so closed flux tubes in this case have been done to too much detail for higher number of colors. I'm not sure whether 1/n squared can be already extracted from there. So we would have to look into a particular observable, and maybe string tangent would be so. So this morning, Michele Catella showed this seminal work of 20 years ago by Sommer and Neko, which computes in SU3 string tension to a very high precision, and then compares with the Nambu-Goto spectrum, and their work also on at finite temperatures, and comparison beyond the Lusher term. So maybe Michele can comment more on that since he has done more of the SUN computations.
Maybe Andreas can also comment on 1/n corrections.
Exactly. Yeah. Hi, everyone. I was actually looking. I mean, maybe I can share the paper of Glubov. I mean, the last paper that we published. And basically, what I can, I mean, because I don't know, I mean, by heart, I mean, the result, but I mean, the question is also related to something that Marek asked in my presentation, and I haven't replied. I mean, and okay, in the plots that I presented, it definitely demonstrates that there is almost no difference in the lattice simulations between SU3, SU5, and SU6, for instance. I mean, so one could say that SU3, I mean, basically reflects, I mean, qualitatively, I would say quantitatively, I mean, also it refers to the large limit. So SU3 is actually quite close to the larger limit. Now, it really depends on the quantity. I mean, different quantities, such as, for instance, global masses, I mean, have different 1/n squared, I mean, prefactors. But this is something that can be, it can be found in bibliography. Actually, I will share with you our last paper where you can actually see how small this prefactor is. Okay, but so one could say, at least for flux tubes, that SU3 really reflects the physics of SUN. N goes to infinity.
Same goes for the dynamical quarks. It's very hard to find the observable where the effect of dynamical quarks is really pronounced. I mean, when one does very precise calculation of involving of some hadronic quantities, then one sees this effect, as discussed also. The seminal Wilson's computation without dynamical quarks already got the results up to 10%. So if one goes to a percent level, only for some quantities one can see it. But then, for example, computation of the
presumably with quarks, the corrections become 1/n rather than 1/n squared, so they could be somewhat more noticeable. I don't know if people have noticed this numerically.
But can one say, that's the question to Marina and to the people who do Monte Carlo. Can one extract really from these differences? Or you say that there are no differences between, say, SU3 and you spoke about SU5, but I saw in papers, tall papers, there are quite huge n's involved in similar calculations. Can one try to extract the 1/n correction by just fitting to the two different data for pure fluid dynamics, for essentially for string tension, but maybe also for masses?
I've seen such fits. Yeah.
It can be done. Actually, let me see if I can share. I mean, such feeds. I mean, so can I share my screen?
I think you're allowed to share. I think.
Let me see. Yeah, I mean, for instance, here you can see the continuum masses of some excitations, global excitations, and this is the mass in units of root sigma as a function of 1/n squared. So actually, you can see that there is this in most of these cases of the states, the slope is quite low. I mean, for instance, for this state here, which is the first excited state of 0++, with 0++ quantum numbers. I mean, it looks quite.
That's flat.
So it looks like. I mean, yeah. So the larger corrections are quite light. I mean, but there are also other quantities where the corrections could be like larger. I mean, let me see if I. Here is another example of masses of tuples with J equals 1, and you can see that this is a continuous extrapolation. Let me see. This is also, I mean, masses of J equals 2 as a function of 1 on the X squared. You can see that there is the slope is small. I mean, obviously there are differences. You can identify these differences, but I mean, qualitatively, let's say, I mean, things don't change much. I mean, as you go to the large limits. Of course, you can identify these corrections. I mean, with quite good precision.
And you go up to which n here, Andreas?
Here we go up
n equals
to
12.
N equals 12, yeah. I mean, it's a bit challenging going to very large values of n because of algorithmic limitations. Basically, the topological charge freezes. I mean, because we lose ergodicity as you move to larger values of n. So one has to be really, really careful there. How to deal with the systematics coming from the fact that the simulation stops being ergodic. So, yeah.
What are the sizes?
I want to make a brief comment to answer Volodya. It depends very much on the configuration you consider. You can think about configurations where you have two junctions or two baryonic and anti-baryonic vertex with NC string between them. This will clearly be very different for different ends. The slope will go like 1/NC and the mass will go like NC. So then it's clear a distinction between finite and larger N. But this is not for the trivial closed string, but rather closed string that include this two junctions or baryonic vertex and anti-baryonic vertex.
Thank you.
Yeah, I wanted to, Victor Garbenko wanted to ask something.
Yes, so one very short comment on the previous discussion, 1/n, that this axion mass, it actually changes a bit from, say, SU3 to SU6, and it's like 10% lower for SU6. So we were hoping that it will go to 0 when n is taken to infinity. But then, I mean, Mike and Andreas actually simulated it, and they measured the axion mass at n equal infinity, and it stays finite, it's stabilized, but it's somewhat lighter than, you know, SU3. So one of the, and also they have this very nice feeds for, I think, 1/n squared corrections to axion mass. Okay, and yeah, the question I wanted to ask is about what are the prospects of simulating, say, supersymmetric QCD, like n equals 1 QCD, which is basically an adjoint massless quark. Because I heard, you know, some people were working even on n equals 4, but then n equals 1 should be a bit simpler. What is the status? And is it feasible to, say, measure, I know, the flux tube, either the closed flux tube or the open flux tube, see for the spectrum of massive excitations? I think it would be very interesting how possible it is.
Yes, a related question is in 3 dimensions also. One can look at that.
Yeah.
Yeah, so as you mentioned, there are some works on n equals 4 super young males, but yeah, so supersymmetric theories on the lattice suffer from something known as the sign problem. So basically, since we need to compute these path integrals by Monte Carlo sampling, then when one has a complex weight, then this sampling is not possible. Here, one doesn't get a complex weight in the setup which is used. So I just let me mention some groups which do that. I probably excluded some, but Simon Cotterell from Syracuse University has been working on supersymmetric theories. Then David Scheich, who's now in Liverpool. Then there's a group in Vienna as well. Andreas Wipp has been active in this direction, and so there are technical difficulties in simulating, because it's possible to do them in principle, but because this Boltzmann weight is sometimes positive, sometimes in rare cases negative, but one has to take this into account when simulating this, and whenever one has a doublet of quarks, then the square is positive if one takes the two of them together in the weight in the path integral. But if one works with a single quark, then there are some difficulties.
But do people have in practice some approximate ways of dealing with this sign problem?
Yeah, so an approximate way is to square everything and then to take the square root and then to monitor the sign of the square root. So it is in principle possible, but it requires it's technically challenging. It requires more work in order to get the same precision in the observables which one would get in the case, for example, of fundamental quarks and SUN, where everything is positive in the bottom, right?
In principle, at least in the continuum field theory, the fermion determinant, well, the Dirac operator has double the generate levels. So extracting square root should not be a problem, at least for continuum field theory. And what happens at the lattice, of course, I don't know. But anyway, supersymmetry involves algebra of supersymmetry involves translations, and lattice breaks translations, so it breaks also supersymmetry. But supersymmetry may be restored in the continuum limit, right?
That's a possibility, yeah. Yes, so to think of a way to redefine the theory such that the continuum limit is the same as the theory which one wants to simulate. But so you're saying n equals 1 would be more interesting than n equals 4, and Igor, you're mentioning that 3 dimensions might already be sufficient, so we wouldn't need to do it in 4 dimensions.
I didn't say n equals 1 is more interesting than n equals 4. It definitely sounds easier, at least, from there are fewer fermions, let's put it this way, definitely fewer degrees of freedom, but I think also very interesting. And the big difference is, of course, that n equals 4 is conformal and n equals 1 is confining. So at least, you don't have a problem of trying to get the fixed point, the conformal fixed point, which may also be started on the lattice. So it's very different, sounds technically easier. So I was wondering if anybody was actively working on it. And it sounds like a very good problem. Also in the equal.
Okay. I've seen papers already many years ago by Montvey where there was some kind of spectrum of bound states given, but I don't know, maybe experts can comment if people are now trying to improve this.
There works, people are working, towards that. But yeah, I need to, I cannot recall, names.
Yeah, so it's not a mainstream, but it's true what Victor said, that lower number of fermions is better than the higher number of fermions. But as I said, so in principle, we can't directly simulate any fermions. We would need to rewrite them as a function of bosonic variables in order to be able to place them on classical computers. So there is also now a very active field of trying to simulate directly the Hamiltonian dynamics, so to perform quantum simulations of these theories. And I think this approach, maybe in 3 dimensions, is something that might be viable in the future. So for larger number of dimensions, one needs large number of qubits in this case if one wants to map the lattice to the degrees of freedom on a quantum computer. But this might be something to be picked up. Also, like if it would be interesting to study it in even smaller number of dimensions, so maybe 1 + 1. If it's already interesting, then this might be something where quantum simulations, so the real-time simulations which do not suffer from sign problem, would be an interesting thing.
I just want to make a point that actually the expectation in 3D is that there are no flux tubes in three-dimensional n equals 1 to CD. It flows to a gapped phase, and there is the confinement.
Mm-hmm.
But I mean, that's something, and there's a very specific topological field theory that should emerge. I don't know if that's, if you put the theory on a torus, you will be able to see the right number of ground states. But I'm saying that you're not going to see a flux tube. Well, okay, that's the expectation.
Mm-hmm.
I see Lance has a question.
Thanks for a nice review, Marina. Can I ask a question that kind of comes back towards Marek's question about hybrid states? But it's like more general in the sense that I think it's much easier to determine the mass of a state on the lattice if it's stable against strong decays than if it can decay, at least rapidly, into strong decays. And these hybrid states always tend to be very close to threshold for decays. And you know, how much do you run into trouble as a function of where you are relative to the threshold? Maybe you could comment on that.
Yeah, that's a very good point, Lance, and yes, that's one of the difficulties. So the approach that we are practicing in this one related to Born-Oppenheimer approximation, it has its systematic uncertainties. I mean, due to the assuming that the heavy quark is not moving, but then these potentials we can determine them very precisely, as you've seen. Now there is the other references which were mentioned this morning by Atoshi Hosaka. They do not rely on the Bornheimer approximation and compute it directly on the lattice, and this is where this question of threshold is very important. In short, we overcome this by working in an unphysical situation, so heavy mass of the pion, and so the lattice parameters are tuned such that we are far away from the threshold. So the results that are obtained in this unphysical setup are stable, and then one needs to extrapolate towards. So in the physical situation with physical values of the pion mass, then this becomes a problem. So it's true what
in particular, maybe there's some non-analytic behavior as you move into the regime where the things are really closer to the threshold because of coupling between the states it's going to decay into. They're really nearby in terms of virtual corrections, if you want to think about it that way.
So you're saying the extrapolation might not work in a sense.
There might be some funny things that happen when you're close to threshold, unless the scatterings are suppressed by I don't know, soft pion stuff. It depends on which channel it is, probably.
Yeah, that's a good point.
I don't know if people have studied that. I'm certainly no expert on it.
Yes, there was a very interesting study of this question by Eske Eichten at Fermilab. You might want to have a look.
Yes.
It's some conference proceedings. Precisely this point, what happens when you have states close to threshold which interact with those above threshold, then the problem becomes quite much more challenging.
Yeah. I mean, there's there's an example of this in some sense even before the exotics. There's the D star. The D star is very close to D pi threshold. And in fact, it depends on which isospin state you are in. And so in some sense, there's a big violation of isospin just because one guy can decay and the iso partner can't because of the way the masses are tuned. I don't know if that was also in the, but yeah, I'll try to find that Eichten paper. Thank you, Mark.
Thanks.
I think another case where it comes up is this H particle, the lambda bound state, which may be pretty close to threshold. I actually saw recent papers from the Lattice, but I think they don't go down to realistic masses of strange quark. But it looks like it's not going to be bound. That's I mean, it's like a many-year story of whether it's bound or not. But
can I make a comment?
I wanted to ask you. I wanted to ask you, Marina, a question about this string breaking that you started to talk with. I mean, can you relate it to the decay processes of excited hadrons? For instance, excited mesons will decay by string break, or similarly for the baryons. So the question is whether this lattice simulation that you are doing relates to what people measure in these decay processes. For instance, depending on what type of quark antiquark pair you create in the breaking point, and how does the probability for this decay processes depend on the mass of the hadron or the length of the string? All these questions, it will be very useful to see whether lattice is in agreement with experiments.
That's really interesting. I mean, short answer, conceptually, yes. In practice, so the approach would be similar. We would just need to take into account larger bases of operators, but in practice, it hasn't been done yet. So that's something we are looking into to understand. But as I said, first in this simplification, which has its issues and systematic uncertainties, the Born-Oppenheimer approach, but then eventually, I mean, it would be great if we would do it also in a full-fledged dynamical setup without relying on approximation. It hasn't been done yet, but yeah, that's something we're thinking about.
Okay, thank you.
She wanted to make a comment.
Yeah, because this issue of the lambda, sorry, the H particles mentioned, and as far as I know, in Japan, the so-called HAL QCD people, they have analyzed these lambda systems in the lattice, and they found that in the SU3 limit, somehow the H particle could be bound, but in reality, with SU3 breaking, they go away. So another comment, issue is that the states very close to the threshold, they can be a very weakly bound state or kind of virtual state, or could be a resonance. I think that this is always the issue for this kind of discussions, including exotic state near the threshold states. And I think one way is to make use of, example, the Flux parameterization, which is quite well known for some time for analyze the experimental data. But this is my personal opinion, but really precisely determine whether the observed peak, the resonant virtual state, near threshold states, weakly bound state is really tricky business. And probably we need still the further mutual discussion between experimentalists and phenomenologists, and possibly with some basis. What is unknown is the basic interaction between the hadrons in the coupled channels. So therefore, in that sense, I guess the lattice QCD would be very helpful to give us an information on basic interactions, especially between the hadrons. Hadron-hadron interaction is in general very difficult to observe in experiment, right? At this moment, my personal opinion is only the nuclear-nuclear interaction has been very precisely now determined, but and now the progress is made in the hyperon interactions in particular, like including the JPAC facility in Japan. So we still have plenty of things that we have to study. Thank you very much. This is my comment.
Yeah, thank you. Yeah, you mentioned actually that your model overestimates the binding of this doubly charged one.
Right.
Can you remind us what the actual binding is there?
20 MeV.
And you got 23, right?
Yes, yes.
So it's very close, actually. Right?
Well, okay. Actually, what they observe is just a few MeV, right? It's very, very tiny binding, but our quark model prediction is 20 MeV. Mm-hmm. So from the, this is the scale of, I would say, nuclear physics scale, the 10 MeV order or something. And from this point of view, this difference, I would say, rather large, is significant. And we need to have some method to improve this. But this is another issue because the model we use, the quark model. So where we need a quark interaction, that is even more difficult to study rather more than the hadron-hadron interaction. Hadron interaction is accessible by the lattice QCD in principle without much ambiguities, but the quark interaction is something very much different.
Okay, I think Gabriel Coma has a hand raised.
Yes, so it's more of a curiosity. It's really not my field, but since there was this comment on the line shape, there is a criterion based on the sign of the effective range to decide whether a resonance is actually a loose bound state or something more elementary. And yeah, I wanted to know if there is, since there is some discussion DD star on this DD star tetraquark, if there is any update on that, how does that compare with the data and the model that was presented before? Is there any consensus?
Can you repeat the question, please?
Yeah, I'm just saying, so Professor Osaka, I think, was mentioning that we just measured the line shape of many of these exotic hadrons, and it's hard to see from there whether these are really loose bound states of two objects or some more microscopic object coming from QCD, as far as I know. So I wanted to know if there's some consensus on this DD star tetraquark. It's just out of curiosity.
Well, we will hear two experts tomorrow who I think will talk about this. That's Thomas Kvarnitsky and Feng-Kung Wong. Thomas is the member of LHCb, which is responsible, the collaboration which discovered this tetraquark. I think it's fair to say that at the moment it's possible to explain it a posteriori as both a tightly bound tetraquark and as a hadronic molecule, because it's so close to threshold. Theoretically, the case of the analog with two bottom quarks is much simpler because the binding is so huge that you cannot obtain it from exchange of light mesons. It cannot be a hadronic molecule. So it might be a mixture. Nobody really knows for sure. I don't think there is a consensus at the moment, but I think tomorrow we'll hear more about this.
Thanks.
Yeah, thank you.
Mara, could I ask a question related to that?
Yeah, sure.
You might think that you could distinguish these two configurations by the relative branching ratios to the relevant mesons versus to, I don't know, J psi, but it might also depend on which channels are open. So are you saying that in this DD star case, you can't use that kind of diagnostic?
There is, Lens, there is no J psi because these are two charmed quarks. It's not a C anti-C.
Sorry, you're right. There's no other channel to signal the C's close to each other because the baryonic double baryon would be way above.
Well, yeah.
It's too bound to make that.
The only decay channel which is available, barely because it's strictly speaking a few hundred kV below threshold, is DD star. What it really does, it decays into two Ds and a pion, and the invariant mass of the D and the pion is essentially very close to the D star. So it's the finite width of the D star which makes it possible.
So at least you can't like use any branching ratio data to diagnose this, but what about the total width? Is that any kind of a diagnostic?
You know, I've learned that
it's too hard to compute, probably. Yeah.
One thing I've learned is that after you have the data, explaining it is almost always possible in your favorite model. And it really makes a difference if it's a prediction or a postdiction.
Sure.
So, but you know, Frank Kuhn, for example, thinks that this is very likely a molecule.
I mean, even the new one, this TCC one.
Yes. And you can certainly construct a theoretical model in which you get this. So it will take a while before we know for sure.
Yeah,
But
for this older one, this X3872, that was CC bar, right? So that to that one, once this question applies.
Right. So let me add to this discussion, since you just focused on this TCC state, which you know, which is a new type of state, but we have plenty of other exotic candidates that have CC bar or BB bar inside, and you know, experimentalists are getting, in some cases, to be able to do coupled channel analysis. This was particularly done for some of Z sub C states, which I suppose, you know, fit molecular interpretation. In this particular case, for famous X3872, there has not been any coupled channel analysis, but LHCb is getting to kind of statistics sufficient to analyze line shapes, but so far this was only done analyzing line shape in the dominant channel. In the future, you should expect some coupled channel analysis of the line shapes that can shed more light. So it's, but there are also, you know, many other hadron candidates, which exotic hadron candidates, which are not at threshold. So, you know, overall situation is probably very complex and involves different types of dynamics, which complicates the picture. So this also divides phenomenological community into different groups, either focusing on one type of states or the other, and you can find evidence for both.
Well, I think, thanks a lot, Tomasz. I think all of this was a really good preview to more discussions and talks about the exotics tomorrow. So unless there are more comments, maybe we should close the proceedings.
I'm sorry, can I make a few comments?
Yeah, okay.
Yeah.
Okay.
I think if we observe, well, general statement, if we observe the peak from the experiment, many theorists tries to build a model and say this is a molecular or weakly bound or resonant and so forth. But to be honest, I think they are just one option. And what we should do is first to identify where the poles are of these things. But the pole analysis is again quite difficult. But we have recently started the neural network analysis, deep learning analysis by looking at the line shape to identify the where the poles are, whether the first Riemann sheets or the deeper second Riemann sheets and so forth. And by doing that, we can say that this could be a virtual state or the quasi-bound state. But so if I say one more thing, say in a nuclear physics case, it's well known that nucleon-nucleon interaction in a triplet S state and a singlet S state. Triplet S state, there is a deuteron bound state. And the singlet S state, although the attractive interaction is very strong, no bound state. But if you look at the cross section on amplitude, the scattering of these two channels looks very, very similar. So just by looking at them, we cannot identify, whether the bound state are there or no bound state. But we recently developed this deep learning method to identify this. And then the important physics message, this is my personal point of view, whichever the difference between the virtual or bound state for this deuteron or NN case is only slight, very tiny difference in attractive interaction. If the attractive interaction is slightly sufficient enough, then the bound state appears. If the interaction is not enough, then it becomes a virtual state. Still, strong attractive force is there. So from the physics point of view, I think that if there is a sharp peak, there is some attraction. So I'd like to know that what is really the cause, origin of this attractive force. Whether this is a bound state or the kind of virtual state, personally, not a very big issue. The big issue is to identify an origin of the interaction. That is my impression. Thank you very much.
Thank you. So Marina wanted to...
Yeah, a short general comment on the baryon spectrum, as Asushi was mentioning that earlier today. So from the lattice, we can also compute this, as you know, and compare in the same way as these model predictions, but such a subtle differences of tens of MeV in order to get them, that's another place where we need to include these isospin breaking corrections, such that we could make this distinguish the subtle differences in the octet and so on. So this has been done already by Zoltan and his collaborators a couple of years ago in a particular setup, and they got the proton-neutron mass differences. But we are currently looking also in the in other other baryonic states, and this is where this inclusion of QED in simulations will also be important, and we hope to be able to get these distinctions as well. So we have some preliminary results there, but in the years to come, I think several collaborations will embark also on more precise computations of the baryonic spectrum, where the charge plays a role as well, and the mass differences between up and down quark.
Yeah, it's a really good point. Yeah, once you get down to MEVs, you have to include them and all that stuff.
Exactly.
Okay, well, I think we're probably everyone's ready for lunch. I want to thank Marina and also the speakers from earlier, everyone, for a very stimulating day. Thanks a lot.
Thanks, everyone.